Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course, Mathematics for Economics. The module that we are covering right now is about difference equations. We have seen in the last few lectures how to solve a first order difference equation which is non-homogeneous. And right now we are talking about certain examples and applications where such difference equations are used. Now, this is the model that I introduced in the last lecture, a market model with inventory. So, here there is a demand side and there is a supply side like in the cowboy model. However, unlike the cowboy model, we are not assuming that the market clears in every period. Here it is possible that there is some excess demand or excess supply in the market and that affects the inventory of the producers, and because of this inventory and change of this inventory, the producers might change their prices in the next period. In particular, as you can see on your screen, the second point that I have written here, if the inventory has piled up, they may reduce the price so that the unintended inventory can be disposed of. Similarly, the price is revised upwards if the inventory has run down unexpectedly. The idea is that in any period, suppose the inventory is piling up, then the producers will like to give some encouragement to the buyers to buy this unintentional rise in inventory. So, in the next period they will reduce the price so as to give incentive to the buyers. And similarly, if the inventory is running down unexpectedly, in that case they will like to stop that run down and they will raise the price so as to discourage the buyers. So, this is how the model is working. Mathematically, we represent this in terms of these three equations. So, like the cowboy model, we are assuming the demand function and the supply function, they are linear. But unlike the cowboy model, the supply function is a function of the current price. And this third equation is the new thing. You do not have market clearance in each period, but what you have is adjustment of the price, and presumably this adjustment is done by the producers. So, Pt plus 1 is equal to Pt minus sigma of Qst minus Qdt. The parameters are all positive, alpha, beta, gamma, delta, sigma. Qst minus Qdt is the excess supply in period t. This denotes the accumulated inventory, the part of the production that is not sold, that will go to the inventory. So, this is that accumulation of inventory, and the new parameter that we have introduced here is sigma. It measures the response of accumulated inventory on the next period's price. So, this is where the lag is coming. So, if there is accumulated inventory, Qst minus Qdt is positive, then that is going to affect, right, the price in the next period, all right. And how much does it affect? That response is measured by sigma. In particular, QST minus QDT affects the next year's price in a negative manner because it measures the excess supply, that is accumulation of inventory, and that reduces the price. Now, these three equations, if we put them together, then that will give us the first order difference equation, and this is how we are getting it. Okay. So, we are basically substituting the demand function and the supply function here in the Pt plus 1 equation, and that will reduce everything to functions of Pt only, right. So, it is a difference equation of first order in Pt, right, Pt plus 1 minus of 1 minus sigma beta plus delta multiplied by Pt is equal to sigma multiplied by alpha plus gamma. Now, I am not going to into the steps of this solution. So, we have to find out the particular integral and the complementary function. The particular integral turns out to be this, like in the cobweb model, alpha plus gamma divided by beta plus delta, and the complementary function is this. This is the complementary function a b to the power t, where if I know that in period 0 the price was P0, right, I use that information. So, this becomes the complete solution. Pt is equal to P0 minus alpha plus gamma divided by beta plus delta multiplied by 1 minus sigma beta plus delta whole thing to the power t plus alpha plus gamma divided by beta plus delta. And to make it look simple, I assume that this P star is the particular integral, right. P star is equal to alpha plus gamma divided by beta plus delta. I assume that. So, I get rid of this cumbersome term. I only write P star, and as you know, P star is the intertemporal equilibrium value of price in this case. Now, let us talk about the stability. As we know that in this solution, the stability of the equilibrium depends on this term, the B term, which is 1 minus sigma multiplied by beta plus delta. Now, as we know, it can take 7 possible different values or ranges of values. However, we can get rid of 2 such values because we know sigma, beta, delta all are positive. Therefore, this possibility that this B is greater than or equal to 1 is ruled out, right, that is ruled out because all these parameters are positive. So, 1 minus these things cannot be greater than 1, all right. But even if we have got rid of 2 possibilities, there are 5 possibilities that are left out. For each of these cases, one can find a condition in terms of the 3 parameters sigma, beta and delta. So, 5 cases are left out, and let us try to see how they turn out to be. So, these are the 5 cases that I am talking about 1, 2, 3, 4, 5. This B can be between 1 and 0, it can be exactly equal to 0, it can lie between 0 and minus 1, it can be equal to minus 1 and it could be less than minus 1. And in each of these cases, these conditions, if we play around with them, then they turn out to be like these. The first region or the first condition turns out to be that sigma lies between 0 and 1 divided by beta plus delta. And this case, as we know, B lying between 0 and 1, it will give me a time path which is non-oscillatory and convergent, right. That comes from our initial results. Secondly, if this is exactly equal to 0, we know we are always in equilibrium because B is equal to 0. And this condition turns out to be this, that sigma is equal to 1 divided by beta plus delta. The third case is 1 minus sigma multiplied by beta plus delta lies between -1 and 0, and this turns out to be this condition, that sigma lies between two limits, 1 divided by beta plus delta and 2 divided by beta plus delta, and as we know, this gives me damped oscillation case. Fourth case is 1 minus sigma beta plus delta is just equal to -1. We know this will be a case of uniform oscillation, right, because B is equal to -1, and this condition can be written as this, sigma is equal to 2 divided by beta plus delta. And finally, the fifth case is the B value, that is 1 minus sigma multiplied by beta plus delta is very low, it is less than -1, and in this case we know there is going to be explosive oscillation, right, and this condition once again turns out to be this, that sigma is strictly greater than 2 divided by beta plus delta. Now, out of these 5 cases, therefore, we have these first 3 as stable, right. In these cases, you have convergence or you are always in equilibrium, whereas the last 2 are not stable. Now, these 5 cases can be in fact shown in terms of a very convenient diagram. In this diagram, what we have done is that along the horizontal axis, we have taken beta plus delta, and on the vertical axis, I have taken sigma. Now, why have I done so? Because if you look at the table, you will see that we are getting these two equations. One is sigma is equal to 1 divided by beta plus delta, this is the case, and here is the other case where sigma is equal to 2 divided by beta plus delta. Now, if I am representing beta plus delta along the horizontal axis and sigma along the vertical axis, these two relations can be shown as two rectangular hyperbola. So, this is the first one and this is the second one. Sigma is equal to 2 divided by beta plus delta and sigma is equal to 1 divided by beta plus delta. Both of them are of the form x multiplied by y is equal to k. That k here is 2 and here is 1, and we know that is the typical equation of a rectangular hyperbola. So, these two rectangular hyperbola will help us demarcate these cases, these 5 cases. As we can see that the unstable cases are these, either sigma is equal to 2 divided by beta plus delta or sigma is strictly greater than 2 divided by beta plus delta. Now, which are these regions that we are talking about? These regions are actually these cases above the higher rectangular hyperbola or even on the rectangular hyperbola. These are the cases where there is no stability. So, that is what I have written here. Below the curve, sigma is equal to 2 divided by beta plus delta, the price converges to the intertemporal equilibrium value. What was the intertemporal equilibrium value? It was that P star, the particular integral. So, if we are picking up points from here, that is below the upper rectangular hyperbola, then we are actually in that region of parameters where there is stability. Either you are always in the equilibrium, or even if you are not on the equilibrium, you are going to converge to the equilibrium. All right. And in other cases, that is if you are on the northeast of this upper rectangular hyperbola, or if you are on that this rectangular hyperbola, there is no convergence. Okay, here is an example of an exercise. Following three equations characterize a model that is a model of inventory, market model. Find the intertemporal equilibrium value of price and comment if there is convergence. Okay. So, these three equations are given: the demand function, the supply function, and the price adjustment function. We have to answer two questions. We have to first find the intertemporal equilibrium value of price. Now, that is given by this formula, right? P star is equal to alpha plus gamma divided by beta plus delta. So, I just pick up the values from here and put it here, and if I do so, I will get 3. Okay. Alpha is 21, gamma is 3, okay, 3, and beta is equal to 2, and delta is equal to 6. I put all of them here and I get 3. 21 plus 3 is 24, divided by 2 plus 6, that is 8. 24 divided by 8 is 3. Now, then we have to answer the second question, comment if there is convergence. Now, we know that convergence depends on this particular expression, 1 minus sigma multiplied by beta plus delta, and again I put the values here. Sigma is 0.3, so I put that value here, and I know the rest of the values, and I get minus 1.4, and minus 1.4, as we know, it is less than minus 1. So, there is going to be instability, right? And it is instability plus it is going to be oscillatory instability because this is negative. The B term is negative and it is less than minus 1. So, there is going to be explosive oscillation. Okay, now we take up another topic of difference equations, which is nonlinear difference equations and phase diagrams. So, if you do not have linear difference equations, then how you deal with them? If there are non-linear first order difference equations, a way to analyze them is to take the help of phase diagrams. Okay, so, we are going to use phase diagrams. So, here is an example: yt plus 1 is equal to 6 multiplied by yt square minus 9 yt plus 4 is a first order difference equation, but it is not linear. First order because the lag, as you can see, is of 1, but there is a power of yt here which is 2, right. So, it is not a linear difference equation, it is non-linear. Now, the first thing to note is that in general such equations can be expressed in this form: yt plus 1 is f of yt, that is a function of yt. Note, yt is the only independent variable in the above function. We plot this relation in a Cartesian plane with yt and yt plus 1 represented along the horizontal and vertical axis respectively, and we demarcate the 45-degree line. This line is of great service in phase diagram analysis. So, let us see if we can find a diagram Okay, here it is. Here is a Cartesian plane, that is two-dimensional plane. On the horizontal axis I have taken yt, and on the vertical axis I have taken yt plus 1. So, it is not xy, but the value of the variable that we are dealing with in two successive periods. The previous period is on the horizontal axis and the subsequent period is on the vertical axis. Okay. Now, additionally, what we have done is that we have plotted this function, right. This function is what? It is yt plus 1 is equal to f of yt. This line, as you can see, it is not a straight line, right, and that is precisely the reason why it is a non-linear relation that we are dealing with. And plus we have demarcated the 45-degree line, right. This 45-degree line will be very critical in the analysis of phase diagrams. Now, why it is going to be critical? Because 45-degree line, along the 45-degree line, as we know, the value of the x and the y, right, the coordinates are equal. So, that is the property that we are going to be using in this analysis. In the diagram, the difference equation yt plus 1 is equal to f of yt has been represented in this plane, Cartesian plane, yt plus 1 yt. It is, in this case, I have assumed to be an upward rising line, right. It is an upward rising line with slope greater than 0. It is not necessary that all fyt's will be like this. There could be downward sloping lines as well. We shall deal with them later on, but right now to start with, I am assuming that this f of yt is a increasing function. At the point where it cuts the 45-degree line, what we have is this, that yt plus 1 is equal to f of yt is equal to yt, right. The y and the x, they are equal because you are talking about this point. In this point you are on the 45-degree line as well. So, yt plus 1 and yt are same at that point. And let us suppose that particular value of yt, it is denoted by y star. So, what we essentially have is y star is equal to f of y star. That is how y star is defined. Now, start from an arbitrary y0 in t is equal to 0. So, what we are saying is, suppose we are starting in the initial period where t is equal to 0. Now, what is the value of y in that period? Let us suppose that is y0, right. That could be any value, an arbitrary value. So, we are taking an y0 like here, it could be somewhere else also. Now, the question that we are asking is, does the time path of yt converge to y star, right. That is the question. That is the question of dynamic stability or the lack of it. On the horizontal axis, we have taken y0 to be less than y star. Now, y0 is here, then the question is, where is y1? Well, that can be easily found out by using this function, right. So, from y0 we draw a vertical line and go to the point of at this curve, and that will give me y1, right, because that is the next period's y, which is determined by the function. So, the value of y1 can be read off from the function yt plus 1 is equal to f of yt. This is marked on the vertical axis since the function f of yt is above the 45-degree line, therefore y1 is strictly greater than y0, right. So, at this point the function is above the 45-degree line, right, it is above the this line, 45-degree line. So, that obviously means that y1 will be more than y0. So, this is y1. Now, the question is, where is y2? We are interested to know the locations of y1, y2, y3, etc., because we want to find out whether we are approaching y star or not, because y star is the point where if you go there, then you will stay there, right. If you are at y star, then in the next period also you are going to be y star, in the third period also you are going to be at y star, etc., etc. So, the question of dynamic stability is, when you are starting from an arbitrary y0, then the sequence of y's, do they go towards y star or not? Do they converge to y star? So, that is why we are interested to find out where is y2 if we know about y1. To find this, we use the 45-degree line. The 45-degree line helps us project y1, which is located on the vertical axis, on the horizontal axis as shown. So, here is y1, I am projecting this on the horizontal axis here. How am I doing that? I am taking this y1 and going to the 45-degree line and drawing a vertical straight line, and I am reading y1 from the horizontal axis, right. So, this is y0, therefore, and on the same line, on the same axis, I am able to locate where is y1. And if I know y1, then I will straight away know y2, because from here I draw a vertical line straight going to the f function, f of yt, and f of yt will give me y2, which is here, right, from the function. And y2 is here, but we wanted to find out what is y2 on the x-axis. So, again I project that on the x-axis taking the help of the 45-degree line. So, here is y2. Okay. So, this is the method we are deploying here. We are using the 45-degree line to project the values on the y-axis, on the x-axis, and simultaneously we are using the f function as well. So, that is what we have written here. From y1 on the horizontal axis, we follow the same procedure as described above to locate y2 on the vertical axis, which is projected back on the horizontal axis with the help of the 45-degree line. Since f of yt curve is flatter than 45-degree line, the increment falls. So, this is very critical, the last statement. The f function, I have purposefully drawn it in a manner that it is flatter than the 45-degree line, at least in the neighborhood of y star, at least where I have located y0. Now, if it is flatter, then it basically means that subsequently the gaps between y's will go on declining. So, what I mean by that is that this gap, the gap between y2 minus y1 is less than this gap, which is y1 minus y0. You can see that with your naked eyes in the diagram, but that is coming because this the f function is a flat function. So, that is what I have written here, y1 minus y0, which was the first increment, is strictly greater than y2 minus y1. This was the second increment. So, likewise you can go one step further. The next stage will be y3 minus y2, and that y3 minus y2 will be further lower than y2 minus y1. We go repeating the steps described above. At each iteration, the successive yt's get closer. That means the gap between the two successive y's, they keep on declining. As can be seen in the diagram, in the limit as t goes to infinity, yt goes to y star. Alright. So, this is how it is happening. First you go here, then you go here, and like this you ultimately reach y star. So, these are the arrows one can draw to show how the path is demarcated. So, in this case there is actually dynamic stability. Thus, in this case there is convergence to the intertemporal equilibrium value. As t goes to infinity, yt actually tends towards y star. One can get the same result of dynamic stability if the initial y is greater than y star. So, here we took y 0, that is the initial value, to be less than y star, but if we had taken it somewhere here, then also the same result would have been applicable. So, here this will be y 1, and from here you can find y 1 here, this will be y 1, and from here you can find y 2 here, this is y 2. So, you can see that actually you go and converge to the point of intersection, which is y star. Okay. So, it does not really matter where we are starting from. Y 0 could be above y star, it could be below y star. In either case we are able to converge to y star. If the fyt has a shape as shown here, here means in this diagram, then however there is no stability. So, let us try to trace out one path. Here we are taking y 0 here below y star. So, y 1 will be in this value, right, and again projecting back we get y 1 here. So, yt will be here, and as you can see y 0 was here, y 1 is farther away from y star, and y 2 will be even farther away, and so we are actually going away from the intertemporal equilibrium value of y. Starting from y 0, the time path takes one increasingly away from y star. The difference between this and the earlier case is, in this case, the shape of fyt is the slope. The slope of fyt is greater than 1, at least around the equilibrium point. That you can see here, this line fyt should not be here. Fyt is a steep line. In particular, it is intersecting the 45-degree line from below, which means that it has a slope which is greater than 1, which is the slope of the 45-degree line. And in this case, we are getting the case of dynamic instability. So, in both these cases, one was stable, the other is unstable. There was one common point, that the f function was an increasing function, right. But what happens if the f function is not increasing? If it is downward sloping, then you have something like this, right. I have drawn this f of yt function. We can see from the diagram that price here fluctuates between below and above the intertemporal y star. So, here y star is at the intersection point like before, which is the the long run intertemporal equilibrium value. But let us see how the time paths look like. So, we are starting from y0 here. What is y1? We go to the f function, this is y1, and we are projecting it back, right. So, this is y1 on the horizontal axis. Now, what is y2? We go up, right, this is y2, and so this should be y2. So, this is y2. But as you can see that price first it was below y star, then it goes y to y1 which is above y star, and then it again comes back to y2 which is below y star, which means price is fluctuating in this case from below to above the intertemporal equilibrium y star. That is the first thing to note, but the second thing to note is that the price over time is becoming closer and closer to y star. So, thus in this case the time path is actually convergent. Unlike the case depicted here, if the absolute slope of f of yt is greater than 1, then the time path will be divergent, right, although it will fluctuate as long as f of yt has a negative slope. So, the reason why we are going to have a fluctuation is because f of yt is downward sloping, that is giving me fluctuation, but whether you are going to have stability or not, that depends on the absolute value of the price. So, what is being written here is this: suppose this is the 45-degree line and you have a downward sloping line, but which is very steep like this. So, in this case you are going to have instability, right. So, let us start from, suppose this is p star or y star, and you are starting from here y0 going up to y1. So, this is y1, this is y1. What is y2? y2 is this. So, this is y2. Okay. What is y3? This is y3. So, as you can see, we are moving away from y star. First we were here quite close to y star, then we are going a little bit away from y star, y1, and then y2. Again the gap is rising from y2 to y star, and y3 the gap is rising even more. So, actually you are going away from the equilibrium, there is divergence. Irrespective of positive or negative slope, if the absolute value of the slope is less than 1, there is dynamic stability. So, this is the conclusion. If we want to have dynamic stability, then the absolute value of the slope of f of yt, that has to be less than 1. If it is positively sloped, you are going to have monotonic convergence. If there is a negative slope, then there can be dynamic stability, but it will be a kind of fluctuation of price. And if the slope of f yt varies between less than 1, equal to 1 and greater than 1, and between positive and negative values depending on the value of yt, one will see complicated patterns of time path of price. So, this is a general case that it is possible that if you have y f of yt, but it is not always less than 1 and not always greater than 1, but the slope goes on changing, right. It can be equal to 1, less than 1, greater than 1, and it can be positive and negative as well. Then we can have really very complex pattern of time path of price. Okay. Just think about it in terms of a diagram. Suppose you have something like, okay. So, you can see first we are starting from a very steep line, but then it is flattening out, and again it is getting quite steep, right, at this stage. So, here the slope is varying between less than 1, equal to 1, greater than 1, etc., right. In this case, like S kind of function, you can have very complicated pattern of price over time. Okay, I think we shall start this discussion of higher order difference equations. Maybe I will not be able to finish it today itself, but at least we can introduce this new topic. Now, so far we have talked about only first order difference equations. There was only one leg, but if there are higher order difference equations, then how we can deal with them. In particular, we are going to talk about second order difference equations. So, here is the general form of a second order difference equation with some additional properties, that this equation is a linear equation, right. It is non-homogeneous because you have a non-zero term on the right hand side, and we have constant coefficients, right. A1, A2 are all constants, and on the right hand side I have a constant term C. So, this is that equation which satisfies all these properties, and we want to find out how to solve it. Now, the general pattern remains the same, that first we find out what is the particular integral and the complementary function, and given the initial conditions we find out the value of the arbitrary constants, and we write the general solution. So, that is the strategy of solving it. Let us first start with the particular integral, and we assume a simple solution yp is equal to k is a constant, and I put it here, okay, yp is equal to k, and so that means y is invariant with time. So, I get this equation, and that boils down to k is equal to c divided by 1 plus a1 plus a2. But I can write this if the denominator is non-zero, that is 1 plus a1 plus a2 is not equal to 0. But what happens if 1 plus a1 plus a2 is equal to 0? Then we have to try some alternate solution. I take yp, that is the particular integral, to be a function of t, k multiplied by t. So, again I put this in this equation, and if I do so and solve it, then I will get k is equal to c divided by t multiplied by 1 plus a1 plus a2 plus a1 plus 2. However, this part drops out because it is equal to 0. So, I am getting c divided by a1 plus 2. So, therefore, the solution will be this multiplied by t, right. In this case, the particular integral will be k multiplied by t, that is ct divided by a1 plus 2. And this is called a moving equilibrium because it is a function of time, right, t is there. But this again is valid if the denominator is not 0, that is a1 plus 2 is not equal to 0. So, I have to cover the case where a1 plus 2 is equal to 0, right. This is the third case. Now, if a1 plus 2 is equal to 0, then we try another solution which is a little bit more complicated. Yp is equal to k multiplied by t square. So, earlier we took k multiplied by t. In the first case we took only k, and now we are taking yp is equal to k t star. And again this can be substituted in the difference equation and solved for k, and we are going to get k is equal to c divided by 2. Therefore, yp is equal to c divided by 2 multiplied by t square, and this is the case where this condition is satisfied and the earlier condition this is also satisfied, right. So, that these two conditions actually will give me these two values, a1 is equal to minus 2 and a2 is equal to 1. So, this is the case of particular integral. As we can see, there could be 3 possible cases. Now, we come to the complementary function, and yc is equal to a b to the power t, right. This is the complementary function that we use, and we substitute it to the homogeneous part of the difference equation, and this was the difference equation yt plus 2 plus a1 yt plus 1 plus a2 yt is equal to c, and this will give me this thing a b to the power t b square plus a1 b plus a2 is equal to 0. So, the first part, that is a b to the power t, is not equal to 0, therefore, only this part is equal to 0, b square plus a1 b plus a2 is equal to 0. This is a quadratic equation in B, right, and this is in particular, this is called the characteristic equation, and its roots are called characteristic roots, and it is given this form minus a1 plus minus root over a1 square minus 4a2 whole thing divided by 2, right. These are two characteristic roots. One, if we take the plus sign, minus can be taken, then that will give me the second root. If b1 and b2 are the two solutions, then the complementary function is written as this: capital A1 b1 to the power t plus capital A2 b to the power t, where a1 and a2 are arbitrary constants. Okay. So, this is the general case, but as we know, there could be 3 possible sub cases from here. One is where the roots are real and distinct, right, where within the square root, this part, that is a1 square minus 4 a2 is positive, that will give me real and distinct roots. Okay. So, let us explore this possibility. a1 square minus 4 a2 is greater than 0. Now, in this case, let us suppose the roots that we are getting from here, right, are called b1 and b2. Then the solution, as we have just seen, is yc is equal to a1 b1 to the power t plus a2 b2 to the power t. So, here is an example. Suppose this is the difference equation that is given to us: yt plus 2 plus yt plus 1 minus 2yt is equal to 1. Here, what is a1 square minus 4 a2? It turns out to be 1 plus 8, which is equal to 9, and which is, as we know, is positive. So, this is the thing that we are talking about. Here the roots will be real and distinct, and as it turns out, the roots are 1 and minus 2. So, this 1 and minus 2 will be substituted here as b1 and b2. So, this was the first case where the roots are real and distinct, and we have seen what is the complementary function in this case. The second case is a case where there is repeated real roots, right. In this case, a1 square is equal to 4a2. So, basically we are talking about this part becoming 0. In this case, there will be no distinct roots, there will be a single root, and that is why we are calling it repeated real roots. And what are these two roots? Actually, they are the same root. It is equal to minus a1 divided by 2, and this root is repeated twice. In this case, yc, that is the complementary function, is equal to a1 b1 t plus a2 b2 to the power t, and since b1 and b2 are same, this can be written simply as a3 b to the power t. And in this case, the complementary function is actually written as this: yc is equal to a3 b to the power t plus a4 t multiplied by b to the power t, where like before a3 and a4 are arbitrary constants which can be found out if we are given the initial conditions. And finally is the case of complex roots. So, this is the case where the square root term a1 square minus 4a2 turns out to be negative, right. So, this is the condition where it is negative. In this case, the characteristic roots are complex in the form b1 and b2 is equal to h plus minus vi, right. I is the imaginary number, where h is equal to minus a1 divided by 2 and v is equal to root over 4a2 minus a1 square divided by 2. So, therefore, the complementary function is a1 b1 t plus a2 b2 t, and I know b1 b2 are these h plus vi. So, I can write them and it turns out to be like this. Now, by De Moivre's theorem, h plus minus vi to the power t can be written as r to the power t multiplied by cos theta t plus minus I sin theta t, where r is equal to root over h square plus v square. In this case, what is h square plus v square? It is simply a2. And what about theta? We have to find out what is theta also. Well, theta is given by this this relation, that cos theta is equal to h divided by r, and if we use the value of h and r, then it is coming out to be minus of a1 divided by 2 root over a2, and similarly sin theta is equal to v divided by r, and that is coming out to be root over 1 minus a1 square divided by 4a2. So, if we solve this, then we can find out theta, and if we solve this, I can find out r. So, then we can put the value of r and theta here. Okay. Now, since this is known, then yc I can just put in place of h plus vi, I can put to the power t, h plus vi to the power t, I can put r to the power t multiplied by cos theta t plus I sin theta t. In place of h minus vi to the power t, I can put r to the power t multiplied by cos theta t minus I sin theta t, and this simplifies to be this r to the power t multiplied by a3 cos theta t plus a4 sin theta t, where a3 is equal to a1 plus a2 and a4 is equal to I multiplied by a1 minus a2. Okay. So, this is my complementary function in this case. Okay, this was the case of complex roots, right. So, we have discussed all the 4 cases of real distinct roots, repeated real roots and complex roots. These are basically the cases where the characteristic equation has to be solved, and the characteristic equations can have 3 separate cases of roots. So, we have talked about that. Now, the next point is to take one particular equation, second order difference equation, and try to solve it, right, where you can have complex roots. So, here yt plus 2 plus 1/4 of yt is equal to 5. You can see that the lag is of 2, right. So, it is a second order difference equation. There is no non-linearity here. So, first we look at that term a1 square minus 4a2, right, that is crucial. So, in this case it turns out to be minus 1, which basically means that the roots are going to be complex. And if the roots are complex, we know that the complementary function we have just found out, it is given by yc is equal to r to the power t a3 cos theta t plus a4 sin theta t, where r is equal to root over a2. What is a2? a2 is equal to 1/4. So, root over a2 will be half. So, remember we are taking the positive root here. And what is cos theta t? We want to find out theta also, right? Cos theta t and sin theta t. So, cos theta is, as we know, is given by minus a1 divided by 2 of root over a2. And what is a1? a1 is 0 actually, because there is no y t plus 1 term here. So, the coefficient of y t plus 1 is 0. So, therefore, a1 is 0. So, cos theta is equal to 0 means that theta is equal to pi divided by 2. So, that information is used to get the complementary function, which is half to the power t, this is the r to the power t term, multiplied by a3 cos pi by 2, right, theta is equal to pi by 2, multiplied by t plus a4 sin pi by 2t. So, this is the complementary function. We still do not know what is a3 and a4, but if we know the initial conditions, then we can find that out. But we have not found out the intertemporal equilibrium. The particular integral, again we take yp is equal to k, and if we substitute that here, then we get k plus k divided by 4 is equal to 5. That gives me k is equal to 4. So, both the yp and yc's are found out, then the general solution will be the sum of these two. That is it. Okay. That is what we have written. If the initial conditions are known, the values of the arbitrary constants can be calculated. Note, as t changes, the values of sin theta t and cos theta t goes on changing in a cyclical pattern, right. So, that we know from trigonometry that as this theta, that is pi by 2 is given to us, as t changes, so cos pi by 2 multiplied by t, right, t will take 0, then 1, then 2, etc., etc. So, this angle is going to change accordingly, and the cos of that angle will change in a cyclical manner, and similarly the sine of the angle will also change in a cyclical manner, right. That is what I have written, it is going to change in a cyclical pattern. The cycles are not smooth because the variable t takes only discrete values, it is a step like cyclical movement, right. So, t will take only values like 0, 1, 2, 3, 4, like that, discrete values. So, corresponding to that, the sines and the cos, they will go on changing like that, according to that. So, the value of yt will change in a cyclical manner, but it is not going to be a smooth cycle, it is going to be something like this. Right. As you can see, there are jumps between two time periods. So, that is what I mean, that it is a step like cyclical movement. All right. So, I will stop here, and in the next lecture I am going to talk about the convergence, right. So, we have talked about convergence and dynamic stability of first order difference equations. We have solved the second order difference equation, the general pattern. But what about the question of dynamic stability, right? Under what conditions dynamic stability is going to be there, that we can discuss in the next lecture. Thank you.